Hi, I'm Slattery. I'm from the University of Puget Sound, and I've worked with Dr. Cecily Sunday, Christine Hartzell, and Daniel P. Lathrop this summer investigating impacts in granular material under the influence of an external magnetic field. Asteroid 16 Psyche is the motivation of this project. It's a relatively large asteroid located between Mars and Jupiter in the main asteroid belt. And it's suspected that this asteroid has a magnetic field. If that's the case, then that would influence how we interact with the asteroid. That's of particular interest because it's also possible that this asteroid has a mainly metallic composition, which is important if we were to, say, mine the asteroid. There's currently a NASA mission en route to 16 Psyche. You can see the probe of the satellite over there. And it should arrive at 16 Psyche in 2029 when we'll be able to see what strength magnetic field the asteroid has. All images of 16 Psyche on these slides are artist renditions because we haven't actually seen the asteroid yet. In my experiment, I used Helmholtz coils in the red over there to produce a relatively uniform magnetic field. We have steel grit in the center of those coils, and we are dropping impactors of steel and brass into the steel grit and measuring the crater profiles that form. The impactors are dropped from a solenoid valve pin system that I built, and they have roughly the same impact velocity of 4.6 meters per second. In addition to the coil setup, I also built a line laser scanning system where you can see the line laser over there pointed down at the steel grit. It's mounted on a translation stage to be dragged across the crater. And finally, we have a camera held at a non-zero angle from the vertical, and we can exploit the geometry between the camera and the line laser in order to develop accurate measurements of the diameter, depth of these craters, as well as the surface roughness surrounding the craters. These are some craters that we've observed through these experiments. You can see at 0 millitesla over on the left. It's a crater with a slightly raised rim, but the surface outside of the crater is mainly flat. Here at 18.4 millitesla, you can see that the surface outside the crater is still pretty flat, but the rim of the crater has actually formed peaks, which are frozen ejecta, where ejecta are the particles that are blown from the crater during impact. At 25.2 millitesla, the highest magnetic field during these experiments, you can see that surface roughness is actually expanded to include the surface outside of the crater, while still maintaining those peaks around the rim of the craters. Steel impactors and brass impactors result in similar craters, so I'm just showing this steel here. These are some crater profiles that I was able to measure from the line laser scanning system. You can see at 0 millitesla, there is that ridge along the edge of the crater. And you can see that between the 8.4 millitesla and 25.2, the ejecta peaks at the rim of the crater are definitely taller than those at the higher magnetic fields. While at higher magnetic fields, the surface roughness has definitely increased up the outside of the crater. These results were further analyzed in terms of surface roughness, where we calculated the expectation value of z squared. Z is the height of those ejecta peaks from 0, which was just the surface of the outside of the craters. And that was plotted as a function of the bond number. These axes are a little bit messed up, but the bond number is down here on the X. The bond number here, you can see which magnetic field corresponds to which bond number. It's a dimensionless parameter telling us the relationship between the magnetic and gravitational forces acting on the system. Over in the plot, you can see that the surface roughness does tend to increase with increasing magnetic field, but there is probably a peak surface roughness that occurs around 16.8 millitesla at high point there. In addition to surface roughness, we also analyzed the depth and diameter of these craters. We noticed that the depth and diameter of these craters tend to decrease as magnetic field increases. This relationship is approximately linear when plotted in terms of the bond number. And again, it's that same bond number that we discussed on the last slide. It is notable that as these linear trends go to 0, it's expected that there is a sufficiently high magnetic field for which there is no crater form, because the granular material will act basically as a solid. Our impactors will actually just bounce off of the material instead of forming a crater. In conclusion, there is still some analysis that needs to be done in order to connect our results and further analysis the bond number to scale up to asteroids like 16 Psyche. But there are some similarities between artist renditions and the craters that we have observed. For example, on the outside of these craters here, you can see that there are indeed ridges that resemble the frozen ejecta peaks of the craters that we observed. One difference is that the rims of our craters appear to be larger than the rims surrounding this crater. We'll have to wait until 2029 to see what other parallels we can draw between. Most asteroids are considered rubble piles, where they're collections of sand and pebbles held loosely together by gravity, and they're not entirely spherical, as you can see from this artist rendition. But again, we'll have to wait until we can actually see the asteroid to determine what shape it is and if it has a metallic composition. Over on the left, that is an asteroid that we have seen. It is Itokawa, and if you're interested in learning more about Psyche and these experiments, please talk to me at the poster session. I'll be more than happy to answer any questions. I want to thank Daniel P. Lathrop, Cecily Sunday, Christine Hartzell, Esteban Wright, Nolan Balu, and Daniel Serrano for their support with this project, as well as all of my peers, both in Trend and all of the other programs here, as well as the Trend REU and NSF, University of Maryland, and my home institution, the University of Puget Sound. Thank you.